This might be a little too loud, but everybody can hear me well? All right. And I have the unenviable task of actually already being over time. I was supposed to finish at 4:15. I do have one good news for you, and that is that my talk is 30 minutes, and I will try to stay on time. And let me just start my timer so that I know when I run out. The title of the talk is An Open Science Approach to Magnetic Resonance Imaging. It will touch on a couple of aspects of my research, but I'll try to broaden it to talk more about what we, as a community, what we in particular as Southeastern Europe possibly, could be doing to advance MR research. And before I do any of that, I'd just like to tell you a little bit about my path. So I'm originally from Macedonia, former Yugoslavia. I went for my undergraduate studies at Stanford. So I was there from '97 until 2009, where I did my undergrad, my master's, and my PhD. And this is the lab where I did my PhD. It's called the Magnetic Resonance Systems Research Lab. As you see, it's a pretty large group. This here is the founder of the lab. His name is Al Makovsky. He just celebrated his 90th birthday, and I was very happy yesterday to see quite a few Stanford folks here who actually know Al well. You know, he's my academic grandfather. This here is a magazine that we did where we interviewed Al, and you'll hear a little bit more about that magazine in a bit. And here's one thing that I learned in this lab. I don't know how many of you do MR research, but the signal-to-noise ratio in MRI is proportional to the square root of the imaging time. That means if you want to increase your SNR by a factor of 2, you need to be scanning 4 times as long. And let me just get metaphorical about this and just tell you that, you know, good research takes some time, just like good images take some time. And I'm somebody who does practice this slow science approach to research. How slow? Very slow. I told you I was at Stanford from '97 to 2009. Guess how many papers I published in that period? 0. It's true. 3 papers seems to be the norm. But then I had one abstract that I wanted to turn into a paper. My PhD advisor said, well, you should calculate the opportunity cost of writing that paper. And opportunity cost means the cost of writing the paper at the expense of not doing something else. And I told John, he's one of the students of Al Makovsky, you know what, I calculated the opportunity cost, I'm not going to write this paper. What should I do next? He said, I don't know. So then I had about a year in which I was just looking for research topics, something that I was excited about. Published a lot of abstracts, but I never felt like they deserve a paper. And John was very aware of the way that I want to do science, so actually he allowed me to graduate without a published paper. The first paper I published came 2 years later, and here it is. It feeds a little bit on my PhD work, but actually the bulk of it came in between the period from the end of my PhD to the start of my postdoc. And it has this very long title, but I consider it kind of like a pre-registration of a study that I've wanted to do for a long time. Basically, what we wanted to measure is a quantity called the G ratio in the brain. It's related to the myelin, to the thickness of the myelin sheath. And this was published in 2011, and it was my first paper as first author. 4 years later, during my postdoc, I actually did the experiment that I proposed to do in this paper. So you can consider this our pre-registration, and you can consider this our experimental validation of the hypothesis. 2015, that's the paper that got me a job. That's the paper that got me tenure eventually. That's the paper that will allow me to do this slow science for the foreseeable future. We published all the data that came with that paper. We said, here it is. You want to share, you want to check, everything is out there and it's available. And then 7 years from that pre-registration in 2011, in 2018, we actually published a review article that said, okay, this is G ratio imaging. In the period from here to here, there's been about 20 replication studies. The paper has been cited over 140 times in about 3 years. And I think it's one possible way of doing science. I'm not saying it works for everybody. All I'm saying is that it worked for me. If you ask me, I wouldn't even have 4 papers. I think this is just all part of one large study, one large paper. Starts with a pre-registration, continues with the experiment, finishes up with a wrap-up that's more of a discussion of the field. So that's just a perspective of where I'm coming from, just to set it up. Now, of course, The talk is about open science. And the word open science, it's a loaded word. What does it mean? It means many things to many people. Some people will argue that it's all about the access to the paper, so it's all about open access. Or maybe it is about the educational resources. Or it's about making your code open source. Or it's about diversity and inclusion. And then there's also the aspect of citizen science, getting regular, everyday people involved in science. No time to discuss too much there. I guess for the purposes of this talk, I'm going to group the open code, the open source, the open data, and the open educational resources together, and call the aspect of open science that I'm more passionate about reproducibility. To me, this is very, very important. So important that I actually just wrote an editorial for the journal Magnetic Resonance in Medicine that was already mentioned, where we spoke about reproducibility and the future of MRI research. Why we think this is very important? Well, because a software developer in my lab did some studies about papers that are published in this journal. Magnetic Resonance in Medicine is probably, most likely, the leading magnetic resonance research journal. It's published by a big society, the International Society for Magnetic Resonance in Medicine, and it has published about 500 papers this year in 2019. Out of those 500, we did some keyword searches to see how many of them attempt to have some aspect of reproducibility and transparency. So we searched for words such as open source, open science, GitHub, Git, Jupyter, Notebook, etc. And we found 174 papers that matched one of these keywords. Out of these 174, 52 actually linked to shared code and data, MATLAB being the most common language. And then only 12% of these actually shared enough to potentially reproduce a figure in the paper. Now, you could argue that this is either impressive or not good, depending on your perspective. But I think this number should be higher. Because of the papers that had any aspect of open science or reproducibility to them, only 12% could reproduce the paper figures, 75% could reproduce an aspect of the paper, and 13% had broken links to code or data, so it was not even accessible. Well, my battle in MRI has been to make these numbers higher. And it's a very broad field, and there's many different topics, and I know that the audience is not very technically MR trained. So I'll just illustrate a lot of these concepts through one technique that is called T1 mapping. Before I explain what T1 mapping is, I'll just tell you that MR images are kind of like a spoonful from an alphabet soup of contrast mechanisms. You have the T1 contrast, the T2 contrast, the proton density contrast, the magnetization transfer contrast, you name it. And then you take a spoonful and out comes an image that we call a T1 weighted image. And this one is just a numerical representation, numbers, where certain values are higher or certain values are lower. You notice that there's maybe a tumor in the image, and that's just something that's bright on a conventional weighted image. Unlike conventional T1 weighted images, you could think of quantitative T1 maps as compartments in a bento box, in a Japanese bento box. Each of these compartments is associated with particular units. So unlike these T1 weighted images that are qualitative, you look at contrasts 256 shades of gray, if you want to call it that. Here, you actually look at numbers associated with units. And these numbers have to be reproducible across sites, within the same site longitudinally. These are our way of making the MR scanner more than a camera, making it a measurement device. Now, this is a good story, right? It makes sense to get these numbers and to be able to compare them across sites, across patients, follow a patient longitudinally. Well, here's a couple of papers that try to standardize this process. This one here, published in 2010, and this one here that we published in 2015. On this one, the first author is Joël Barral, last author is Dwight Nishimura, again from my lab, old lab at Stanford. And on this one, 5 years later, I'm the first author, and this is my PhD supervisor. The first paper has been doing really well. It's been cited quite a lot, but you see that it had a very long learning curve. It took a while for people to recognize that this is an important paper because it standardizes the measurement. This one went a little bit faster, In fact, so fast that it became one of the top 5 papers in the journal MRM in the year that it was published. Why am I so happy about that? Because this paper is a negative results paper. It shows that we have a problem in the field. And I'll expose the problem, and I think you will be able to grasp it without much of MR physics background. These are 7 different papers, different sites, that claim to do T1 mapping in the brain at 3 Tesla. And these are the values that they report. There's 3 different techniques. One is called inversion recovery, the other is called look locker, the other is called variable flip angle. Doesn't really matter. What matters is that the numbers that they report go from 690 all the way to 1100. That's a variation of about 70%. Now, we claim that T1 mapping is good because it gives you numbers. It has also been around for about 70 years. It's been around since the beginning of nuclear magnetic resonance, which even predates imaging. And yet, 7 papers reporting such big variations in white matter at 3 Tesla, where we know that the peak is very narrow. We have a problem. So we said, let's do these 3 techniques, and let's run them on the same subject in the scanner and see what happens. So this is my brain. No need for de-anonymization there. I'm allowed to make my data public. This is the inversion recovery map. This is the look locker map. This is the variable flip angle map. Just qualitatively looking at it, they're different. How different are they? Well, the variation is about 40%. So even with the same subject, in the same session, in the same scanner, we have this variability in the T1 parameter.
It was the same time?
Yes?
Your brain was too much hotter.
You know, that would be true if it was a very RF intensive sequence, such as magnetization transfer. That would be true if it was a phantom. But this is me, a subject inside the scanner with sequences that are very, very RF. The duty cycle is very low. And this is something that was done in several different subjects. And it's actually something that's been replicated in other studies. So you're right. Temperature can cause this. But you could alternate the order of these if you want to test that, and you will still see the same. Inversion recovery is always in between look locker and variable flip angle. So unless these 7 papers also had the same order, you know, inversion recovery, then look locker, then variable flip angle, and observe the same kind of drift, it's very unlikely that it's temperature driven. Because this trend is very consistent with the trends that we observe in 7 other papers. In phantoms, you're right. In phantoms, that would make a big difference.
You could try to make the same scanning for more periods of 3 hours apart or the next day.
So I have been scanned, how many? 20 times at least, in many different sites. Again, you know, it's not something that we would miss. And again, I haven't ever kept track of the order in which it was done, but it really is, there's no need to do the inversion recovery first. And yet the trend is always the same. Inversion recovery in the middle, look locker underestimating, variable flip angle overestimating the values. So here's another paper that showed this. And this is establishing intra and inter-vendor reproducibility of T1 relaxation time measurements with 3T. This is a paper that was published just this year showing the same trends. And one of the things that they noticed is that there was a bias in the T1 relaxation times, 8 to 10% higher on average when acquired in the Philips scanner compared to the Siemens scanner. So not the 40% variation that's between the sequences, but even just the exact same sequence in 2 different scanners, they will give you different values. So how can we talk about T1 mapping when the numbers don't compute the same way? If you think this is just a problem in brain mapping, let's move on to cardiac. It's the same story. We've written a book chapter here talking about the fundamentals of T1 mapping. This is a paper in vivo that reports differences between sequences for native myocardial T1 mapping at 3 Tesla. And these are seconds, so definitely no time for heat up. And yet, they observe very good agreement in phantoms, but very bad agreement in subjects. Depending on the sequence you choose, you will get very different numbers. Now, the scary part about cardiac T1 mapping. Brain T1 mapping has been around for a while. Nobody uses it for diagnosis. Cardiac T1 mapping, people actually use these numbers to diagnose a condition. And this is a problem if the numbers are never the same. So we published a preprint called Let's Talk About Cardiac T1 Mapping. This was our attempt to do for cardiac what we had done for brain, expose the problem. And this paper was called by one reviewer irritating, and by the second reviewer, on a scale from 1 to 5, 1 being the worst paper ever, 5 being the best paper ever, it got 1 worst paper ever in every single category. I don't think it was that bad. And I think it really touched a nerve. This is a field that is very non-transparent. There's lots of conflicts of interest. And as a result, it's very difficult to talk about the problem. What makes it even more difficult, I don't have access to these sequences on the scanner. They're a black box. I don't know what the manufacturer is doing. The manufacturer changes the processing code between versions. They don't share the code. The people who have developed these sequences, some of them, but not all, share the code. So it's up to me to try to re-implement what they're doing and try to make it more transparent, which is what we tried to do. This is the experiment. And then this is what these 4 sequences looked like. So again, we tried it in the same ex vivo pig hearts. And here we observe the same trends. Inversion recovery being very different from the 3 cardiac T1 mapping sequences. Just to show you how drastic this difference is, you will see that depending on which T1 mapping sequence you use, regardless of which time point you image, you will see a drop in the T1 values based on the sequence that was used. This analysis is all available. People can rerun it. The data, the code, everything that we could make available, we have. And at this point, I'm not resubmitting to another journal. I think it's fine. The paper is there. Maybe at some point, if we have some new data, we will resubmit. But to me, it's just a passion project where I think if we need to actually use quantitative MRI, we better make it more reproducible. So hopefully I've convinced you that we have a problem. Now the question is, how do we solve this problem? Well, one solution is to create transparent workflows, ways of connecting the acquisitions to quality control, to pre-processing, and to actual fitting of the data. Now, provenance is the key word there. I need to know how this data came about so that I can deal with any problems or any artifacts that come from the images. Adding some statistics is also a good thing, and we've published quite a lot of abstracts. Again, keep in mind, I don't like publishing papers. I publish a lot of abstracts, where we show that we do have these robust workflows for comparing quantitative MR techniques. How are they implemented? They're implemented under a piece of open source software called QMR Lab. And our goal is to put quantitative MRI under one umbrella. Consider it an app store for MR. And the analogy we're drawing here is, you know how cell phones have advanced. For a while, it was all about the technology. And then eventually, it became about the service. They could no longer compete on hardware. It's really difficult. Hardware in MR is also very expensive, and advances are slow. So more and more, MR vendors want to make these techniques for post-processing available in the scanners, except very little of it is transparent and open source. Our tool is fully available on GitHub. People can contribute to it. People can fork it, do their own modifications. This is the team that works on it. Aga and Tommy are PhD students in my group. Matthew is a software developer we hired. Tanguy just graduated. Julien is a co-PI. Ilana is a collaborator from McGill, where I did my postdoc. And Bruce Pike is my postdoc supervisor now at Calgary. How can we make this work? Well, we need to engage with industry. In particular, we're engaging with a Stanford University startup, HeartVista, that was started from my old lab. And we're working with 2 vendors, Siemens and GE, so that we can make QMR Lab deployable on an MR vendor. The key here is HeartVista. It's a company that produces a real-time imaging system that can bypass any of the proprietary sequences and consoles and take over the scanner and run it from their own console. The nice thing about that console, it is open source, and you can actually have a plugin that can open the door to other applications. So then you can trigger a QMRI workflow, and you can generate quantitative maps at the scanner site. What does that mean? Well, it means that we have a vendor-agnostic approach. Here's a Siemens scanner, and here's a GE scanner. The brains that come out of the 2 scanners are similar, but they're not the same. And this is important even in qualitative MRI, because we've heard a lot about AI. We've heard a lot about ways that these images get pulled together so that you can do analysis. Vendor bias is very well known in the AI community, and anything that we can do to overcome it is a good thing. But when you actually want to go from these qualitative images to quantitative images, that's where this platform that we're developing becomes essential. Here's RT Hawk. That's the Hard Vista company that can run both scanners using the same sequences, performing visual quality control and evaluation of the scans using one graphical user interface. And then here is our open source software, QMR Lab, that can process all of this data so that when you actually produce the maps that come out of the scanner, they will be the same maps, be it on Siemens or on GE. This is a pipe dream. It's a very ambitious goal. Initial results are encouraging, and what we want to do is we want to make it easy for other people to try the same techniques, the same sequences on many different sites. How did this come about? Well, it came about from a piece of software that we published called QMT Lab. This was my first paper that I published as a senior author. And this is the graphical user interface that hasn't evolved much. It makes it easy for people to rerun a lot of the analysis for the papers that I showed you in the past. And then eventually, the 2 PhD students and the software developer that arrived, we agreed that we will make QMR Lab our biggest, most ambitious project. Yes, question?
Are the companies okay with this? I mean, can't they just create a law that can, you know?
So it's a fine line we're treading. Hard Vista is okay with this because what they're saying is, yes, sorry, the question is, are companies okay with this? Could they just at one point outlaw any kind of this bypassing that we're doing? It's true they could. So what we want to do is we want to convince them, look, this doesn't remove any of your existing code. It only adds more. It's an app store. It's kind of like, you know, would Apple want to remove apps from the App Store? Yes, when they come up with sleep tracking, they'll probably remove some sleep tracking apps. But there will be so many more that people will actually want to use them, and they will want an Apple product to run them on. So it's true. At some point, Siemens could say, no, 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 we're not supporting Hard Vista. But actually, Hard Vista started on General Electric, and it's about to be deployed on Siemens. We're one of the 3 sites. So in a way, it's moving in the right direction. Doesn't mean it will keep going that way. All right? So, yes, please.
When I take the same brain, the same thing on a Siemens and on a GE and on a Philips and on a different machine, are these images related by just a pixel lookup table difference, or they are related by some local averaging?
Yeah.
So, the question is, could I get Philips's image by applying a function, a monotone function to the GE image and things like this, and therefore the problem is much worse?
So I'll repeat the question. Can you map one image to the other? Is it a transformation that's easy to do? So short answer, no. Longer answer, if you have the exact same sequence and you know exactly what the hardware is doing, maybe for 2 sites for 2 different scanners. But to do this bulk and make sure that there's always a proper transformation, no, because they have different parallel transmit utilities. They have different setup for the shimming gradients. It's so many moving parts that it's really not easy to do unless you really controlled everything and you were the person that designed the protocol from scratch on both sides.
You cannot do it then either. I worked on tomographs at LC on the hardware side. My first job. The resonance, the reflections from the different plastics, from everything else will distort the image.
Complicated distortion.
Actually, you could detect who made the image by extracting these hidden artifacts.
Yeah. And why are the images not calibrated by scanning a drum tube? So you have a little tube of fat and a little
Beautiful.
tube of water. I do the same for calcium concentration.
Yeah.
Chips with different concentration, we calibrate the CT. You could do the same for the MRI.
Yes, you could. And this is something that we're advocating, actually. There is the National Institute for Standards and Technology. It has developed a standardized phantom because it needs to be the same one. It needs to be at all different sites. Now, phantoms are not as bad as in vivo. So what you would also need is you would need a human phantom to go around. And there is a beautiful success story of T2 star mapping in heart for diagnosing thalassemia, because it was the same person who designed all of the protocols across all of India, and they actually managed to do a diagnosis based on a number. Now, again, this is something that is difficult to do, and it had to do with a lot of calibration and the same people getting scanned.
You know, I apologize for taking work.
Yeah.
Even as you cannot take the two identical pictures with an iPhone and the Google phone, or with an iPhone 7 and iPhone 11, which is 1,000 times simpler
Yeah,
photo.
yeah.
So imagine that multiplied by 1,000 to get exact same.
Good. You know that you've made the point when you actually become the devil's advocate of your own point. No, it's very difficult. Of course, I agree with all of you. It's really a big problem for the field. And I just wanted to kind of say what you could be doing. And all of these approaches, you maybe had another one, could work, but not fully.
The problem a bit more. So you're using this kind of piece of hardware that is extracting the data and not putting it through their pipeline of post-processing. Isn't that pipeline of post-processing on their hardware essential?
Not really. What you want to do is you want to take over the hardware and run it your way. So what we do is we bypass the console, we design our own sequences, open source, and then we run the same sequence using the hardware from GE and Siemens to produce as similar images as possible. Okay? So,
You're extracting kind of like a raw image.
exactly, as raw as possible. If I could get K-space would be ideal. Let me do my own reconstruction, let me do everything by myself.
Like sensor agnostic, actually. That's
Fair enough, fair enough.
hardware is underneath, right?
Exactly. Because even within vendors, there will be variability. So yes. And again, I'm not saying that you can 100% remove the variability, but you can do better than what we currently observe. Yes?
They're saying that the enemy of fluid is wanting to be the best.
Sure.
So I'm sort of asking myself, if you feel that all the machines are going to be really synchronized, it's not feeling as radiologist study. Then I'm not so worried that it's not exactly the same. One is, do they all go in the same direction? So let's say that one machine is 5 and 10, and the other is 50 and 100. Then I just live with that.
Yeah.
So is it, so I think what we need to aim is not, I don't think it's realistic to think that everything is going to be exactly the same. But I would want to be a little bit sure, or surer than I am now, that the direction is going the same way.
Yeah. So two answers. Two answers for your question. One, yes, you as a radiologist, I absolutely agree with you. You would much rather, at least you know the bias and, you account for it by yourself. Sure. But AI algorithms are very incapable of doing that. So this is one reason why you would want to do it. The second answer is, I don't care about every single site doing this. It's far from my point. My point is to say, look, if you really care about getting the numbers right, there is a platform for doing it. Some will care and some will not. And I imagine it's going to be primarily a research tool for a while, and then eventually it might become a radiologist tool. But it's not a mandated thing. It's just I'm saying it is possible. I can do this, and everything is open source and transparent. Now, there's 1 minute and 40 seconds, and I haven't gotten to the community building part of this. I will not run over. I do want to just show you a couple of more things. But honestly, this conversation and this back and forth, it's golden. I'm the last person speaking. I got to engage with so many of you. Screw the couple of slides that are left. That's OK. I think I've made the point across. So this is QMR Lab. Forget about it. It's fun. It's great. We can do fun things with it. Let me talk to you about science communication. This is something that is very near and dear to me. To make these points across, you need to build a community. And building a community is not easy. All of these standardizations, they're 20% technical and 80% social. And part of the reason that I'm here today is to show you a couple of things that I've been doing with the MRI community in North America and in the Balkans, and hopefully get a couple of you to talk to me and maybe join the efforts. I'm on the editorial board of a journal, Magnetic Resonance in Medicine. I've been a guest editor for a special issue in Neuroimage on microstructure. But I also run a couple of blogs. I founded the blog of the Human Brain Mapping Organization, the blog of the International Society for Magnetic Resonance, and mrbalkan.org, which is a local conference for MR professionals in the region. There's also the Canadian Open Neuroscience Platform. This is something where I lead the communications aim. It's a pan-Canadian $11 million grant, and I've gotten about 500,000 of those to develop a publishing platform. These are the committees that are on that CONP. This is a blog post that we talked about where we can go further and how we can catch up with the changes that are happening in the publishing world. This is a new publishing platform that makes it easy to have PDF-compatible documents, kind of like what we've been doing for the last 300 years, but then also make the documents interactive. Add a layer where you can explore the phenomenon, interact with the real-world data, see the code that generated the output, and actually run the code from the notebooks where this output is generated. Looks very similar to the Mathematica story you heard yesterday, right? And it's beautiful, isn't it? I mean, I think this is the way we should be doing science. Not every paper needs to do this, but I'm very happy to tell you that it is possible. Now, it's using Jupyter notebooks rather than Mathematica. So, Jupyter notebooks are open source, Mathematica is proprietary software, but it's the same vision where we can add transparency to the process. So that rather than jumping through these hoops of data acquisition, pre-processing, analysis, and then finally publishing, make that a walk. You don't rush, but you incorporate cutting-edge company technology, open source software, open source Jupyter notebook technology, and these pan-Canadian open neuroscience grants to make something that's a little bit more innovative in terms of how we communicate our research. Lots of things play against us. It's very difficult to convince people to do open science, but we do have a strong community. This is magnetic resonance in medicine. This is all the people that have contributed to a magazine that we publish. This is what interviews with authors of papers in this journal look like. We have some pictures, we have some videos. We try to make it easy for people to relate to the humans that are behind the science. We have some interactive figures. We also have some fun screenshots of people that are very big names in very relaxed settings. Brain mapping, another big group of people that contribute to these efforts. We write blog posts. Sometimes these blog posts get picked up by the New York Times. It's always nice when this happens. It happened about 3 years ago in a post called, "Do you believe in God, or is that a software glitch?" And social media is key. This is how the message gets passed on. So we do a lot of YouTube interviews, we do Twitter, we do Facebook, trying to reach as broad an audience of researchers as possible. We have an event at in Montreal. It's called Open Science Beer. It happens every week. And this is our 1-year celebration at a conference called Neuroinformatics in 2018. And then we had a bigger celebration in 2019. We had about 100 people here. We had about 1,000 people here just a couple of months ago in Montreal. The Human Brain Mapping Conference is coming to Montreal next year. Maybe some of you will be there. We'll do something even better. I think it's very important to get the young people to believe that there is a mission here and that there is a way to change the world just a little bit. We did a marathon. We're calling it an M-marathon. That's my T-shirt. You can't see it because of my arm. We organized this in Montreal in May. It's another way to get people to contribute open source code. And this is the conference that I just came from. I was in Sofia. We had our 5th MR Balkan meeting. The first one happened in Ohrid, Macedonia. Second one also in Macedonia. Third one in Turkey. Fourth one in Slovenia. 5th one in Bulgaria. 6th one, who knows? Maybe it will be Romania. Haifa. Are you Balkan? I think you could qualify. We'll extend the definition. So this is my lab. Julien Cohen-Haddad and myself. We're co-PIs. It's really a nice environment to work with. If anybody is interested in visiting us, I'm happy to arrange a visit. This is the campus of the University of Montreal. The name of our lab is Neuropoly, just like Monopoly, the game. You will not forget it now. That's my Twitter account. And these are all the people that have been involved in these community building efforts. So I want to acknowledge them and thank you for your attention.